Hi everyone, I'm Alice Angley from AusIMM in Melbourne, Australia. I'd like to thank everyone for attending the live webinar today and those who are viewing this recorded webinar. This webinar has been organised by the AusIMM Metallurgical Society. So we'll now start the webinar. Over to you, Tim.
Thanks, Alice. Good day, everybody. For those of you who don't know me, I'm a metallurgist with an interest in statistics. I've worked for many years at the JK Centre at the University of Queensland, which is a research centre, and I've had an interest in stats for a long time and have found over the years it's such a powerful body of method that I've spent a lot of time trying to persuade other people to use the techniques. So that's really what I'm going to try and do today. So welcome to a gentle ramble to what I hope will be some interesting and compelling ideas about why I think that robust statistical methods are not really optional for our profession. And by our profession, I mean metallurgists, mineral engineers, chemists, and like-minded people. And I'm going to try and explain why I think it really should be in our DNA. I've called it rather provocatively the Drunken Mans Lamp Post, and this comes from a quotation by the Scottish man of letters Andrew Lang. Andrew Lang said rather a long time ago, he, by which he meant, by the way, a politician, uses statistics as a drunken man uses lampposts for support rather than illumination. And I guess the case I want to make today is that statistical method, we should be using it to illuminate the problems that confront us rather than using it to support previously held prejudices. So that's really what it's all about. So there are 4 things I want you to take away from today, and I've added one, by the way, since the original blurb went out. The first is all we have is data. It's the currency of our professions. The second takeaway is, unfortunately, all data has uncertainty, and we'll talk a lot about that in the next few minutes. This uncertainty has consequences that have to be managed. The third one is that humans are bad at interpreting data and judging sophisticated risk intuitively. Simple risks are easy to judge. If there's a lion heading for you, you can work out that that's a really bad idea and run away. But if it's a more sophisticated kind of risk, we're not so good at that. But the good news is that statistical method has solutions for all these problems, which I hope to demonstrate. So let's jump in straight away and look at this statement about all data has uncertainty. This is a dot plot of 124 repeat assays of a single zinc concentrate sample. It's actually a standard that was being used in an assay lab on an Australian-based metal operation. And if the world were perfect, all we would see there is one column of 124 dots at the true zinc content of that material, which is, as you can see, around about 56%. We don't see that. We see a distribution, and that is the uncertainty. That is what's called experimental error, which drives all the problems that we face when we analyze data. You can plot that, of course, as a histogram, and you can fit something called a normal distribution to it, and many of you will be familiar with that. The distribution with a central peak that coincides with the mean, which is indeed around 56%, and a standard deviation. And the standard deviation measures the width of this curve. So the wider the curve, the more spread out the data is, the larger the standard deviation. So there's the distribution of 124 results. Now we can convert that to uncertainties by calculating this very simple term, which unfortunately statisticians call error. It's a really bad word because to you and me, error means a mistake. This has got nothing to do with mistakes. It's a direct measure of uncertainty. You can take each of those values and subtract from it the nearest we have to the truth. The truth is the mean of all the data. And you can do that for all those 124 results, and you can plot that as a histogram, and guess what? It's essentially exactly the same histogram, except this time it has a mean of 0 because some of your uncertainties, your errors are below 0, some are above 0, and the mean will always be 0. So those are what statisticians call errors, and it's that confounds our life. Without those, we wouldn't need statistics. Now, the thing about errors is that they're assumed to have two important properties. They're random and they're normally distributed. What random means is that if after 124 measurements you took another of these materials and ran it through the assay lab to check your assay quality, there is no way to predict what that next value will be. The error will be random. You hope it'll be close to the truth, which is 56%, but it'll be somewhere in that distribution. So that's the first property. The second property is that errors are assumed to be normally distributed, which, by the way, these are. The reason that that's important is that a lot of the statistical techniques that are so useful to us, which I'm going to touch on, assume that errors are normally distributed. Well, I don't know if you know Nassim Nicholas Taleb. He's a very interesting guy. He's a statistician and an economist in America. And he's the guy who introduced the term black swan, which is a rare event which has a large impact. So an earthquake or the global financial crisis would qualify as black swans. Well, he said a random series will always present some detectable pattern. In other words, there are patterns. We're very good as human beings at identifying patterns in the world around us. That's what our evolution developed as a skill to cause us to survive. But unfortunately, we see patterns in randomness, which gets us into trouble. And I want to show you a couple of very simple experiments, which actually you can do yourself, which demonstrates this rather well. The first is a coin tossing experiment. I've done this many times with students and other people that I teach. And this is a record of an actual experiment that I conducted a few years back. So I asked two students in the audience, masquerading as human beings here, as you can see, to invent a series of 20 coin tosses. To, in other words, write out what they thought was a random series of tosses of coin with heads and tails. And then I gave two other students a 20-cent piece each. I'm not sure I've ever got them back, actually. And this is what they produced. So I asked them to toss the coins for real and to write down the sequence of heads and tails which they got. So the first two are synthetic invented random series, and the second two are real random series. Now let's look at the patterns, and the best way to do this is to look for runs. A run is a sequence of heads or tails. Here are the runs in the synthetic series. There are only three of three elements or more, and they just happen by chance all to be heads. Now look at the runs that you see in the real series of random numbers. First of all, there are twice as many, and secondly, they're twice as long. There's a run of 6, there's a run of 4, there's several runs of 3. So what does this tell us? It tells us that we're really bad at judging randomness. We're nervous about putting patterns into randomness because we think it shouldn't be there. Whereas the real random series, the coin tosses, show that such patterns do occur completely by chance. And if you hear me use the word chance for that, read error in data. Now let me show you another picture. No, your screen hasn't gone strange. It is a page with lots of dots on it. Just stand back a little bit from that screen and just let it come to you. Watch the screen for a little while and see what patterns you can see there. If you watch for a little while, patterns will start to emerge. So I'll show you what I saw. So here's a line down here. Right through the middle, there's another line. It's actually a gap, interestingly. Up here is another line. Down here's a cluster. Up here, a gap, another gap. And here are some circles. You see these circles? And here are more circles. Now, the point about all that apparent structure and patterns is that, of course, I'm sure you've guessed, these points are completely randomly distributed across that screen. And you can do this in about 30 seconds in Excel. Just go into Excel and ask the random number generator in the little stats toolbox, which I'll come to in a minute, to generate 2 columns of 10,000 random numbers each between 0 and 1, and then just plot them. And this is what you'll get. You'll have to make the symbols small enough for it to show up like this, but you will get a whole series of these randomly distributed points. And yet in each of these, you will find patterns. Those patterns are completely ephemeral. They have no basis other than chance. So again, we're not good at judging chance events. Remember, a random series will always present some detectable pattern. I don't know if you're a Dilbert fan, but even he's got into this issue. Here he is going on a tour of the accounting department of his company, where the random number generator produces a number that doesn't look very random. And when he quite rightly asks the question, are you sure that's random? The answer is a beauty. That's the problem with randomness. You can never be sure. And that's the entire point of why statistics is so important. So let's go to some more real data. This is actually still invented. I actually synthesized this data, but it has all the characteristics of data from a concentrator. Imagine this as 2 parallel circuits. One is running with a mean of about 82% recovery, the other a mean of about 80%. We've got 60 results, so if they're daily results, this is 2 months. The standard deviation of the data is low. It's only 1% recovery. It is correlated because parallel circuits in a plant will always produce correlated data because they're treating the same feed. So the statistical characteristics of these 2 series are correct. They're what you see in a concentrator, except that there's very little noise. There's very little experimental error because we have a low standard deviation of the data. Now, I don't think there's any doubt that anyone looking at that, if you were looking at that, you would be quite confident in saying to the boss, well, we've got 2 circuits running at different recoveries. One's consistently above the other, and we've got about a 2% difference between them. That's fine. You don't really need a statistical tool to confirm that. But let's look at a more realistic standard deviation where the noise is much larger, 6% this time. Now, it's the same, exactly the same process was used to produce that data, except that the noise that was built into the randomness is much higher. And by the way, there are plenty of concentrators with standard deviations that high. The average is about 3 or 4, but 6 is not unknown. Well, now I think you would agree that just by eyeballing it, there's no way you could confidently say that one is better than the other. As I'll show you later on, a statistical tool will let you prove it to a considerable degree, but eyeballing it, you can't. And that's the problem with experimental error. The noise gets in the way of the decision. Let me now move to another metallurgist tool that you will all have used, or many of you who are metallurgists will have used, the grade recovery curve in batch flotation. Very useful tool because, of course, it quantifies the trade-off between concentrate grade and recovery. This is real data from a platinum concentrator or PGM concentrator. Con grade grams per ton up the y-axis, recovery along the x. Doesn't matter which way around you plot those. This is the average of a certain amount of data, 3 concentrates. So this is a batch flotation test in the lab. Now, grade recovery curves are very useful, and our purpose as metallurgists or mineral engineers is to push the whole grade recovery up, because that takes the whole concentrator to a better place. Most concentrators, of course, as you know, run along grade recovery curves, but what we're trying to do is push the whole curve up. Now, supposing you do some experimental work in the lab and you get a new grade recovery curve, perhaps you're using a finer grind or a new reagent, and there's the new curve. Now, if you look at that, you'll find that if that's a true representation of what's going on, there is some improvement. There's a few more % of recovery to be got from that set of conditions over the previous one. But the question that you must get used to asking all the time, it's an irritating question, but you must ask it. Is that really different? Or are we just looking at the consequence of noise, experimental error? Well, we can answer that question with this data because there were plenty of repeats done, as you'll see in a moment. And from those repeats, we can calculate error bars or technically they're called confidence intervals, on the original data. And there they are, error bars both for recovery and for concentrate grade. They are the 95% confidence limits on any one result based on some repeat results. And I think you'll agree they're really very wide. And in fact, we can draw around that a zone of uncertainty. So the zone of uncertainty says that our best shot is the line in the middle, but it could be anywhere in that zone. Now I'll put back the new grade recovery curve, and I think you'll now agree that it would be a courageous individual who would say that is genuine improvement. It's just within the experimental noise. So the question arises, how do we tease out the significance of these differences when we're confronted by these sorts of problems? Well, let me show you the original data. This is data from one of the most extraordinary experiments I've ever seen. It was done many years ago by a PGM company in South Africa. And for reasons that are lost in the mist of time, they asked one of their experienced MET technicians to conduct over 50 repeat batch float tests, identical batch float tests, same ore, same grind, same reagents, same conditions. And this is what he got. So that's real data. And that is a dramatic demonstration of the uncertainty in all the data that we ever collect. And it was that data that allowed me to construct those error bars that you saw earlier. And if you think this is unusual, it's not. This is the norm. The uncertainty with this data is a little on the high side, but it's absolutely not unusual. Where does that error come from? Well, you could write the list down: sampling, feed prep, grind, in other words, assaying, the operator, machine, time-based effects. These last three you could probably call the float test. Now, each of those contributes uncertainty in varying degrees. And actually, we can determine how much each one contributes. Let's look at one of them, assaying. So assaying is done in the assay lab, whether you do it yourself or whether you get a contracting organization to do it. Let me show you the data from that test. So this is the average data for all of those. I think there were 51 repeats. So we've got three products: feed, concentrate, and tailings for the final recovery point, the last float. There are the assays from the assay lab. These are averages. And here's the standard deviation of each assay. Now, where does that come from? The assay lab have done thousands of these before. They've done lots and lots of repeats, and they've got a little formula that gives them the standard deviation of an assay as a function of the value of the assay. So the largest standard deviation comes from the concentrate, the smallest from the tail. Now, let's use the two-product formula to calculate the recovery. There are better ways to do this, as many of you will know, in a batch float test, but I want to use this formula to make a point. So what we now want to ask is, how do the uncertainties in these assays propagate through this formula to the calculated recovery of 69.2%? The question you must keep asking is 69.2 plus or minus what? Well, the good news is a little bit of maths, which I won't trouble you with now, and a little bit of arithmetic gets you the answer. We have to work in variance space. The variance, of course, is the standard, is the square of those standard deviations. And if we work in variance space, we get these results. There are the three products. And here are the variances that each of those contributes to the uncertainty in the final figure. Remember, these are due only to uncertainties in assays. Now, the reason we're using variances is because they add up. It's really simple. So the feed is 1.6, con is practically nothing, the tail is 1.8. You add those up and you get 3.46. That is the variance due to assay uncertainties, the variance in that final estimate of 69.2. The square root of that is the standard deviation, which is 1.86. And note how that variance is distributed. The concentrate, despite the fact that it had the highest standard deviation, contributes practically nothing. and the rest of the variance is distributed pretty evenly between the feed and the tail. So if you were to ask the chief chemist to try and produce more reliable assays, you wouldn't bother about the concentrate, you'd ask for better feed and tailings assays. Now, how do we turn that into a true uncertainty on that recovery figure? 69.2 plus or minus what? How do we get the what? Well, let's go back to the original data. We had 51 repeats, so you can put that in a column in Excel and ask Excel to calculate the variance of those 51. Turns out to be 10. So that's the total variance of all of that data. Now, how much of that comes from assays and how much of it comes from the test itself, which is the rest of the source of uncertainty? Well, the assay we've just calculated, 3.46. And because variances are additive, you can add them up and subtract them, it's very easy, then the float test variance must be 10.05 minus 3.46. There it is. So really, with very little work, given the original data, we now have a pretty good handle on the total variance, where it comes from and how it's distributed. About a third of it comes from assays and 2/3 from the test itself. So the final step is to take that and turn it into a confidence interval or an error bar, if you like, an uncertainty. And here's how it's done. So remember, recovery is 69%. The standard deviation of all that data is the square root of the variance. Square root of 10.05 is 3.2. And we can multiply that number by about 2. The exact number is 1.96 to get the 95% confidence interval on that recovery figure. That 1.96 comes from the properties of the normal distribution, by the way. The answer is plus or minus 6.2% on any one test. So if you did another test, another batch float test, similar conditions, we now know that the recovery you calculate by a two-product formula would have an uncertainty of plus or minus 6%. Now, to the experienced metallurgists and mineral engineers amongst you, that might seem a pretty horrific figure, and it might be a bit of a surprise. Well, let me tell you, you better get used to getting surprised, because that is not unusual. Base metal figures might be a little bit less than that, but they're all of that order. So the recovery is not 69.2%, it's somewhere between 63 and 75. It's that sort of range. Well, what do we do about that? Well, there are several things you can do. You can run a better experiment, you can get better assays, but the easiest way is just to do repeats. Because if you do 2 repeats instead of just have 1, you divide the variance by 2. And if you do 3 repeats, you divide the variance of the mean of those by 3. And similarly, you divide by the square root of 2 or 3 if you're thinking in terms of standard deviation. So what does that all mean? 3 repeats, divide that 6.2 confidence interval by the square root of 3, because the standard deviation is the square root of the variance, and that gives you plus or minus 3.6%. So we've almost halved that uncertainty by doing 3 repeats. And that is why many companies that I work with and I'm aware of mandate that batch flotation testing be done in triplicate at the minimum, because the average recovery you get from 3 repeats has a reasonable uncertainty bound on it. So where have we come from? We've acknowledged there's error in data, but this is a way of calculating that error in an understandable form and developing a strategy for dealing with it, which is repeats. Let's stay with the issue of uncertainty in data, but let's look at trend lines. So here's a graph, which I kindly got from Chris Greed at Magato. So Chris is interested in the impacts of surface chemistry on flotation. This is some of his data, which plots the surface coverage of iron through an EDTA extraction technique as a function of the pyrite content for several ores, 4 in this case, from the same site. Doesn't matter what X and Y are, this is data. Have a look at it. It's curved, isn't it? In fact, if you got Excel's trendline tool to put a polynomial through that, you'd get a pretty good one. And you might settle back and think, okay, that's that's the trend, and so we must go away and manage our affairs accordingly. But if you were knowledgeable about these things, you would probably say, well, hang on, that doesn't look quite right to me. I would expect something like a linear trend, not a curved one. So let's fit a straight line through it. Well, that's a bit of a disaster. And in fact, you can show statistically that that straight line is not a significant straight line at all. It would be much better to put a horizontal line and say that the iron surface coverage is constant. Actually, I've been a little bit naughty. I've been having this conversation with you, having left out one of the points. And here it is, right over to the right, which changes everything. Now we can put a straight line through it, and that seems much more plausible. So what's the lesson there? That 1 point can make all the difference. And 5 points to generate a trend is not a lot of points. But it also tells us something about experimental error. Where's the error here? Well, there's error in every point, but there's also error in fitting the line, because the line doesn't go through the points. So there's some uncertainty. Those of you who know about R squared will know that if the line went through the points, R squared would be 1. Well, clearly it's not. It's a lot less than that. And although the trend might be useful, it's nevertheless got uncertainty in it. So that line has uncertainty. And of course, the line is fitted using a method called the method of least squares, as some of you will be aware, which is built into the Excel tool. And what that does, it minimizes the sum of the squares of these distances, the difference between the point and the line. So it chooses a line that minimizes the sum of the squares of those differences. Now, those differences are called residuals, but they're also errors. I mean, they're exactly the same as what we called errors a little while back. So what's the implication of this? Well, the implication, just as we were seeing earlier, is that there's uncertainty in that line. Where is the line? You could imagine an infinite number of lines that kind of would fit that data. There's only one line that fits it by the method of least squares, which is why we use it. But there's uncertainty there because of the residuals, the errors. And it's really bad news because we've got relatively few points, only 5. The uncertainties are very large. We can actually calculate the uncertainty on any predictions from that simple model, which says that the iron surface coverage is equal to 0.02 times the pyrite content plus about 1. What's the uncertainty in the prediction? Well, here they are. Those red lines are the 95% confidence intervals for prediction from the model, which are pretty horrific. So if you had a pyrite content of 20, you might infer that the iron coverage would be about 1.5 units. And that's our best guess. But the uncertainty is very large. It's anywhere between 0 and 3. Why is that uncertainty so bad? Because we've only got 5 points. And it just flows from the fit of the line. So again, we're suffering from this pesky experimental error that I talked about before. Well, one of the solutions, of course, in fact, the only solution is, because error doesn't go away, it's inherent. The best way to deal with it is to do good experiments in the process of collecting our data. Mark Twain is believed to have said collecting data is like collecting garbage. You must know in advance what you're going to do with the stuff before you collect it. And that's really good advice. So often we rush about with enthusiasm, collect lots of numbers, stick them in a spreadsheet, and then scratch our heads and say, what happens now? No, it's the wrong way around. You've got to work out what you're going to do before you start. And in fact, the greatest statistician that ever lived, R.A. Fisher, who developed a lot of the techniques that are in the Excel toolbox, he said something a bit similar. To call in the statistician after the experiment is done may be no more than asking him to perform a post-mortem examination. He may be able to say what the experiment died of. So again, he's pleading for people to plan, to do the right experiment, and then in a sense, the data analysis takes care of itself. By the way, you don't need to call in a statistician. Our professions are all numerate. We're Excel drivers. You can learn this stuff. You don't need to call in somebody else to help you out. So what do we mean by good experimental design? By the way, don't panic about the word design. That sort of implies you're going to do a trial or an experiment. You sit down for days and and work out some convoluted, mathematically justified arrangement. No, no, no. It's all been done for us. People like Fisher and his mates did all that a long time ago. The experiments that work for us, we know what they are. It's a very small list, and all we do is we choose from that list the appropriate experiment for the objectives at hand. So that's not a big deal. But what do we mean by a good experiment? Well, here's the definition. It's an arrangement of tests, or runs if you like, which has the maximum chance of reaching the right conclusion in the minimum time. And time is money, so that's the minimum cost. It sounds simple, doesn't it? But it's a good trick if you can do it. When you run a trial or an experiment, metallurgists, which is my trade, we're normally looking for an improvement. We are working to get the concentrator, the process plant in a better place. So we're always planning experiments that test some new approach, a new reagent, a new bit of gear, a new circuit. And whenever we do that, the key question is this: is the effect I've observed, the effect is the improvement, is that real, or has it arisen by chance? Because, of course, of the presence of the experimental error I've talked about. Another way to put this is, what's the risk of me making the wrong decision? What is the risk of going to the boss and saying, yes, let's spend the 10 million because we're going to get a 1% improvement, and then we spend the money and we find out we've got nothing? What's that risk? And of course, you will appreciate immediately that there's a link between these two words. Risk in decision making comes from the chance events, the random error that you are fighting all the time when you're trying to tease out the trends that you're interested in. And it's this problem which statistical method addresses and for which it provides solutions. There are two brilliant but simple ideas that underlie good experimental design, and you actually intuitively are perfectly familiar with these already. The first one is what I've already mentioned: repeats. If you don't do repeats, you have no measure of experimental error, so you can't allow for it in the analysis of the data. In fact, if you're familiar with the formula for the standard deviation, in the denominator it has n minus 1. If n is 1, then n minus 1 is 0. You can't divide by 0, so you can't calculate a standard deviation. And essentially, none of the normal statistical method will work, apart from some particular techniques that I won't discuss here. So repeats are crucial. The second brilliant idea is randomization. You know intuitively that if you were doing batch float tests, as you can see in the picture there, you would not get technician Bill to run 3 repeats on reagent A and technician Mary to run 3 repeats on reagent B, because you might just be testing the difference between Bill and Mary. That's not a good experimental design. Equally, you probably wouldn't test reagent A on Monday and reagent B on Tuesday, because something that you have no control over may have changed. The solution to this, which was realized very early in the piece when these techniques were being developed, is randomization. You take the experiments that you have to do, the runs, and you distribute them randomly throughout the experimental space. So the order in which you do them is random. The best example of that is doing a paired trial. So if you're, let's say, testing 2 reagents in a concentrator, so you run A for a while, B for a while, the best way to do this is in short duration pairs. For example, day shift you run A, night shift you run B. Then you toss a coin and say, right, for the next day, which comes first? Answer B, then A. Toss the coin. B, then A. Toss the coin. A, then B. So you've got a string of pairs where the A and B order is random. Really simple idea, very powerful consequences, because it removes any consistent systematic trend that might be there that you have no control over. So these are really simple ideas, but they have very great consequences. Well, what impedes good experimental design and analysis? I've got a rather eclectic little list here that might surprise you. The boss, Now, 20 years ago, this was a really serious problem. It's less so now, and there are many honourable exceptions. But taking this stuff into our DNA requires a culture that supports it. That comes from the boss. So if the boss says we don't do it that way here, he's forgotten, or she has forgotten all the statistics they ever knew or never knew any, don't want to look foolish. Often the solution is, no, we're not going to do it the right way. We'll do it the way we've always done it. Now, as I say, the situation today in 2019 is better than it was 20 years ago, much better, but sometimes it can still be a problem. The second problem is time. I'm going to show you in a moment how to calculate how long an experiment should run for. If you do that calculation and you say, I haven't got enough time, let's say I require a month, I'm going to do it in a week, don't bother. Because if you do it in a week, you won't get the answer that limits the risk of making a mistake. It's much better that you go off and do something else. It's essential that you do the right number of tests. The third problem is ignorance. That's not a criticism. It just says that some people know about this stuff, some people don't. The good news is that as a numerate Excel driver, you can learn all this stuff. And the last one is a very human failing. If you do an experiment in the lab, let's say with a new reagent, you get a 2% improvement, then you do a plant trial to prove it, everybody's expecting to get an improvement. You are, the boss is, the reagent supplier is, everybody wants that. And then if it turns out that the results are showing that that expectation is not going to be met, everyone's disappointed, and it produces some subtle but very powerful pressures. And often what happens is that people are selective with the data. They leave out inconvenient points. And if you think that's not done, I can assure you it is. So there are 4 things to keep an eye on. They're all soluble. That's the good news. They're all soluble. Now let's talk a little bit about this question of how many repeats do I do, and therefore how long will it take? There is a formula. I'm not going to trouble you with it today, but it's easy to put in Excel, and that formula allows you to draw these curves. Now, what are we drawing here? The y-axis is the number of pairs needed in the kind of paired experiment I spoke about a moment ago. And if you're doing 1 pair a day, that's equal to the number of days. Along the x-axis is the effect we're looking for, the improvement we want to detect. The curve is for data, plant data in this case, that has a natural standard deviation of 2%. You can just take historical data and work out its standard deviation, and that's it. That's on the low side for most concentrators, but there are some concentrators that look like that. Now, those mysterious numbers in the top right-hand corner, the power and the confidence level. The power of an experiment is the chance that you will correctly identify an improvement with a confidence of 95%. By the way, those 90s and 95s, you can choose those numbers. These are typical numbers, which is why I've used them, but there's nothing magic about them. So I'm going to say that again. The power of an experiment is the chance of correctly detecting an effect, a change, an improvement at a given confidence level. So this is a 90% chance of detecting that improvement with a confidence of 95%. And the formula needs that information. So what does this curve tell us? Well, if the improvement we think we're going to get and which will justify the expenditure is 1%, we're going to need 35 pairs. End of story. Don't do less than that. 35 is what's required to meet all of these criteria, which is 35 days if it takes 1 day. Now, here's the equivalent for a 3% standard deviation on the data. So this is a noisier plant, right? It's got more data uncertainty, more data error. And this is actually closer to normal for most plants. Now, if you want to detect 1%, you need 80 pairs. It's a very nonlinear relationship. The good news, however, is that if you're expecting a much larger change, of course, it's a much larger effect. You don't need nearly so many pairs to do that. And in fact, if you're looking at 3% or above, it's always less than 10, which is a very simple experiment. Now, these kinds of calculations are really important because if you don't do enough experiments, enough repeats, enough pairs, you run the risk of either failing to detect an improvement that's there or simply getting the wrong answer in one form or another. And so the risk of decision making is compromised. But let me assure you, this is a very easy calculation to do, nothing complicated about it. So as we know, as metallurgists, sample size is king. We know that when we sample rocks, we know it when we sample slurries, and guess what? It's just the same when you sample data. A large sample increases confidence and reduces the risk in decision making. So stats is risk analysis. It quantifies the risk of being wrong in making a particular decision. If you say, I'm 95% confident we've got an improvement, what you're saying is there's a 5% chance I'm wrong. That's a risk I'm prepared to take. You will never reduce the risk to zero. The great thing about stats is it quantifies that risk. Now, this is a risk that is managed. We can see what the risk is, but it's being managed. Here's a risk that's not being managed. It's the same risk, but there's no attempt to design an experiment that deals with that. So stats does the job of putting the bars on the cage. That's really what it does. And no one in their right mind, I think, would go for that right-hand version rather than the left. So I'd like to make the case to you that no one in their right mind would get into an experiment, especially a large-scale plant trial, without planning it as a statistically robust exercise. Let me show you a real trial that went terribly wrong. You always learn from mistakes. So this is a flotation reagent trial in a copper concentrator. It ran for several months. They just switched from old to new at kind of irrational intervals. So they started new for a few days, went to the old one, new for the few days, back to the old one. Originally, it was supposed to run as week on, week off, but you can see that sort of structure deteriorated. And there was no real statistical planning. It was just let's get some values for the new and values for the old, see what happens. Well, this is what happened. At the end, they did what's called a two-sample t-test, which is perfectly legitimate to do, which tests the significance of whatever improvement they saw. The improvement was small, but 0.6%, but if it's real, it's real. And the t-test said we're 94% confident that there was an improvement. Doesn't quite reach the conventional level of 95, but you know, what's 1% between friends? It's good enough. However, this conclusion turned out to be completely wrong, and here's why. What I've done is plotted here the recovery, which they were monitoring, against the feed grade. Now, many of you will know that in concentrators, if you do plots like that, you will see these trends. Generally speaking, the recovery will increase when the feed grade goes up. I've plotted it here for the two different reagents, and I've put a trend line through each of them. And the first thing you should know is that statistically, those two trend lines are the same because of the uncertainty in the lines. They're not significantly different. And you know, we have a spreadsheet that can do that for you rigorously using statistical criteria. So the conclusion of this analysis is that there's no difference between the reagents once you model out the effective feed grade. So the t-test, which is legitimate, said there was a difference. This says there isn't. There's a dilemma. What's actually going on? And if you study this picture, you will see what's going on. Look at the high feed grades. They're all blue points. They're all with the new reagent. Look at the low feed grades. They're mostly red points with the old reagent. And of course, we know that at high feed grades, you get high recoveries. At low feed grades, you get low recoveries. So yes, they did get an improvement when running with the new reagent, but it had nothing to do with the reagent. It was driven entirely by feed grade. And you might say, well, what bad luck? Well, you would be amazed how often exactly this problem comes up. How do we solve it? By doing a properly conducted paired experiment that I talked about a while back, because in pairing, you subtract out these common effects. They go away, and what you're left with is just the real effect. So in this particular case, sadly, they took 5 months to get the wrong answer, and they could have just taken 2 months to get the right answer. And that answer would have been disappointing. There would have been some expectation bias there, but don't shoot the messenger. If the test is properly done and properly conducted, then you must believe the result, even if it's disappointing. So no improvement. However, if you've done a good experiment, then analyzing it in the correct way, and most of those calculations are quite simple, can give very profound conclusions. Let's have a look at the data we looked at earlier. So here's two parallel circuits. One could be running one reagent, one another, let's say. There's that noisy data. Now, that is actually a paired experiment, because each day you've got a pair of results, one in A and one in B. You can use something called a paired t-test, which is in the Excel toolbox to analyze it. I won't go into the detail, it's quite simple. And we can produce some very powerful conclusions that pretty much make the decision a no-brainer. And here are the four conclusions from that actual data set. Number one, we are extremely confident that circuit A produces a higher recovery than circuit B, despite all that noise. Number two, the difference is 1.8%. Well, that's easy, that's just the averages. However, I'm sure by now you're asking 1.8% plus or minus what? And the answer is plus or minus 1%. It's a very simple calculation. So we're 95% sure the truth is somewhere between 0.8 and 2.8. And the final conclusion to me is the clincher. It's the most interesting, the most powerful. It's very easy to calculate, but nobody ever does it because they're not aware of the formula. It's a very simple formula. And here it is. We're 95% confident that the increase in recovery was at least 1%. At least 1%. That's the worst case scenario. The way to interpret that is to say, well, if 1% produces enough revenue to pay for the change, then it's a no-brainer. In fact, we'd be delinquent in our duties to the shareholders if we didn't implement that improvement, assuming it met the usual company investment criteria. That's a really useful number. We can never get confidence to 100%. We can never get risks to 0, but 95% confidence, a risk of 5% is regarded as satisfactory. And at the 5% risk, we've got at least 1% improvement. Now, look at that. That's a very full, comprehensive set of conclusions backed up by rigorous statistical analysis from a very simple, properly conducted experiment and a trivial analysis. That analysis would take you on a slow day, 2 minutes. Once you get used to it, 30 seconds. So this stuff is not difficult, assuming you've done the right experiment. Now, let me look at one quite different trick using some of the experimental stuff that's available in Excel. Statistical control, generating a control chart for a concentrator to warn you when the process is diverging or out of control in some way. So here's some real data from a nickel concentrator over a number of months, ranging from 55 to 75% recovery, roughly. Now, we used Excel's regression tool to generate a multiple regression model. So that's 1y many x's. Here it is, using the measurements that the plant actually made. So recovery at time t, let's say at day t, is a function of the throughput, tons per hour, the feed percent nickel, feed percent sulfur, the square of the feed percent sulfur, because there's some curvature in the relationship, and a little trick here that makes a better model. Don't worry about that. Now let's have a look at how well that fits the data, and the answer is really well. So the pink is the model predictions, and the dark blue is the original data, except for some points down here which I actually left out of the data for a very good reason, which I'll explain right now before we did the modeling. Now, what can you do with that model? Well, one thing you can do, of course, is predict what's going to happen a week on Tuesday, assuming the miners send you what they promised, which is always a big question mark. But if you know what's coming in and you know the conditions, then you can make a pretty good prediction on what your recovery will be. But what I want you to look at here is the use of this model to generate a control chart. So here's the original data. We can now take the model and plot on this plot the confidence intervals on the model predictions, and we call them 3 sigma, 3 standard deviation upper and lower confidence limits. This is typical control chart language. And the argument here is that if a point sits within these limits, then the process is in control. It's doing what the model said it would do. If there are any points outside the limit, and here they are, that's an alarm. The chance of a point being outside those limits, if the plant is following the model, is about 0.1%. So these are very unusual points. If you get the odd one on its own, it's probably not important, but when you get a sequence of them, that's very important, and this allows you to understand that they are special points and they need investigation. There may be a problem that you have to deal with. Now, that's a control chart. They're well known in manufacturing, very easy to construct here. You develop the model, and then it's simple arithmetic and plotting. So it's a really neat little tool. Talking of production trends, here's some data from a base metal concentrator, recovery against over time, a couple of months of data. Somebody in the concentrator said, I think that I get a feeling that we've got an increase in recovery, and it started at some point. So we don't know how much, we don't know where. Well, there's a thing called a cumulative sum plot, or Q-sum plot. Some of you may be familiar with. Very, very simple to do in Excel. It's not in their toolbox, but it takes you about half a minute to set it up. Literally, it's very, very easy. And here's the Q-sum plot of the same data. So this y-axis has units of recovery, but these values have no importance. The important thing is to look at the gradient of the plot at different places. So if the gradient is negative, then the process is running at a recovery below the overall average of the data. If it's positive, the process is running above the overall average, and if it's horizontal, it's at the overall average. And of course, you can see straight away what this tells you is where and when things change. So a change of gradient means a change of mean recovery. And clearly, going from a negative to a positive gradient is a significant change, and that's an increase in recovery. And you can pick the exact day 31. And that might be, of course, a plant trial where we switched conditions. It might be something that was completely unexpected, and we'd like to go back and find out what happened. It might be an ore type change, for example. It might be anything. So it's a very useful trick for adding additional confidence to plant trials, but also to doing forensic studies of processes. And it's easy enough, of course, to just take the averages and work out the magnitude of that change, 2.5%, quite a lot. All right, I'm coming to the end. Let's just remind ourselves now, what can we use statistical method for, and in particular, the toolbox available in Excel? Well, we can choose efficient experiments or plant trials that do the job for us. We can analyze them appropriately. We can compare conditions, equipment, circuits, reagents, and all the rest of it. And we can do all this with a known chance of being wrong. So we're controlling the risk. We can predict plant performance from models. We can do forensic studies of process failures. We've got lots of quality control tools for assay labs and met labs, and lots of other stuff, but all of them lead to decisions with a known risk. And that risk you can get as low as you want. If the risk is too high, we say, no, we're not going there. If the risk is low enough, we can say, yes, we are going there, and we'll make an improvement. Those of you who are familiar with Excel's toolbox will know where to find it. If you're not, go to the data menu, look along the ribbon to the right, you'll see data analysis, click on that, and it'll open up this toolbox. If it's not there, go to add-ins and check the box, and it'll come back. There's lots of tools here, and some of them you'll never use probably, but some of them you'll use all the time. And here are the ones that I think are quite important and useful. Trend lines, of course, you're all familiar with those, 1Y, 1X. But its regression tool gives you lots of useful statistics, both for simple models and also for multiple models, 1Y, many X's. Descriptive statistics, confidence intervals that we've talked about, t-tests which compare means, f-tests which I haven't talked about, they compare variances. So you can say, has the noise in the data got less or more? We've put in a new control system, has it reduced variability. And a thing called an analysis of variance, which is very useful for all sorts of things, but particularly quality control in laboratories, and so on and so on, lots of other stuff. So let's get back to the 4 things I want you to take away from this little chat. Number 1, all we have is data. We don't have any other assets as metallurgists, mineral engineers, chemists. All we have is data. Unfortunately, all data has uncertainty. This has consequences for decision making. Humans are not good at this stuff, doing it intuitively. We need help. We're not good at interpreting data and judging sophisticated risk intuitively. But the good news is Stats has solutions for all these problems, and that's why I believe that getting on top of simple statistical method and good design is not an optional extra for our professions. It needs to be in the DNA. So that's it, folks. Thank you for surviving that long. I hope you found that interesting and thought-provoking. I'm very happy. I know there are some questions now, Alice, that people can send in, and we'll do our best to answer them. But after that, if you want to go away and have a think about it, if you've got particular questions, issues, suggestions, I'm very happy to have a conversation with you by email. So jot my email down there, and it'd be good to be in touch. So Alice, that's it. Over to you.
Perfect. Thank you so much, Tim, for a great presentation. Just a reminder, if you would like to ask questions to Tim now, just write them in your question tab in your control panel. We do have a question for you, Tim. First one. Can you explain the difference between a confidence interval and a prediction interval?
Yeah, great question. If we're talking about regression analysis, a prediction interval is literally what it says. It's the uncertainty in the prediction from the model. The confidence interval, and this is language you just have to get used to, the confidence interval is the interval on the line itself, which is usually much narrower. So that says where is the line, and you can draw a little confidence interval, and the line is somewhere in there. The prediction interval is always much wider, and there's some subtle reasons for this, which I won't go into now. It's quite a different calculation, but it really comes back to the fact that the line is a consequence of lots of points, and the prediction interval is a consequence of only one point, so you have much less certainty in making the prediction. I hope that answers the question.
Yes, fantastic. Thanks, Tim. Another question for you is, you've mentioned Excel a few times. Are there better packages to use for non-statisticians?
There are lots and lots of very good specialist statistics packages. The reason I go droning on about Excel is because all metallurgists drive Excel, and it's got a pretty good tool set. I use, for my professional work, I use a package called Minitab. Why do I use it? Because I stumbled into it many years ago, and it works for me fine. So I'm not saying it's the best in the world, but it certainly works very well. And there are plenty of others, at least half a dozen. There's a language, a statistical language called R, which is freely available, but which you have to do some coding for yourself, which I'm lazy, so I didn't want to do that. Minitab does a very good job, and there are several others.
Perfect.
But I don't think you need, sorry, I don't think you need a specialist package to start with. But there's no harm in using it. The only problem is you've got an overhead in learning to just find your way around the menus and all that kind of stuff, whereas you already know how to use Excel. That's the only issue there. But I wouldn't at all discourage you from using one of the specialist packages.
Perfect, thank you. Another question for you is, what is an acceptable R-squared in trend lines or regression analysis?
Yeah. Well, let me quickly say there is no magic number. I've met lots of people who say, well, of course, I never take anything under a 0.9 as being any good. It's got to be over 0.9 before I believe it. Well, that's, with all due respect, nonsense. R-squared measures the proportion of the total data variation that is explained by the regression. So an R-squared of 0.9 says 90% of the data variation that we see is explained by the regression, and the balance, part of that's experimental error and part of it is model inadequacy. So the other thing you must understand is that the less data you have, the higher R-squared will be. It'll go up artificially. So think about 2 points. You've only got 2 points. All you can do is draw a line between them. The r squared, as you know, is 1. And that's because we haven't got enough points. Now, if you add another point and it's not on the line, r squared will come down. So just because you have a high r squared, it may just be that you haven't got enough points. But I have done really useful work, or colleagues and I and customers and I have done really useful work on plant models with r squareds of 0.3 or 0.4. If the model is statistically significant, which is easy to see in Excel's output, then it's always better than nothing. Always better than nothing. The higher the better, but don't be frightened away by low r squareds. If it does the job, it's fine.
Perfect. Another question for you is, doing repeats cost time and money. How can we justify that?
Well, that's of course absolutely true, and I hope I've made the point in the talk that if you don't do repeats, you have no information that allows you to make informed decisions. The key thing is to have an inbuilt estimate of experimental error. Otherwise, you don't know the enemy, you don't know what you're fighting. And to be more rigorous about it, the statistical techniques that are in the toolbox and which you can learn to use require an internal estimate of experimental error. So that can only come from repeats. So yes, they cost time and money, but it's very important to understand that that is time and money extremely well spent. The alternative is to make decisions and draw conclusions that are simply unsupported by the evidence.
Great. Another question for you is, I've seen reference to p-values in statistics. What are they?
Yeah, P stands for probability, and p-values you'll see scattered all over the place. If you use some of Excel's tools, there are p-values popping up everywhere. The p-value is the risk, actually. If you do an experiment and you're trying to decide whether you've got a 1% improvement or not, a p-value will pop up. And basically, if that value, we use the conventional figure of 0.05, is less than 0.05, you can say the risk of being wrong is low. We will therefore accept that that's an improvement. The complement of that is the confidence level. So a p-value of 0.05 corresponds to a confidence level of 95%. So if the figure is 0.05 or less, we are more than 95% confident we have an improvement, and therefore you can make your decisions accordingly. So p-values are the outcomes of what's called hypothesis testing, which all these tests, t-test, f-test, analysis of variance, regression, they are all hypothesis tests. I won't go into the principle of it now because it just takes a little time to get your mind around it, but it's a brilliant idea that was invented many decades ago, and the p-value is what a hypothesis test delivers. You can think of it as the risk of being wrong.
Perfect. I think we have time for one more question. Why is it that the Q-sum plot horizontal bar values, as shown on your slides, is not relevant? What does it exactly represent?
Well, it is relevant. Let's just get back to it. This particular data set really had, I'm using it because it's nice. It has three periods in the data. The result when it was running lower than the average, then running higher, and then the horizontal one, it runs at the average. So there was clearly another change here. I didn't dwell on that, but something changed at this point here, around about day, 46, 47. And that might be worth looking at as well. And of course, because it goes from a positive gradient to horizontal, that means the recovery went down. It went down at that point. And it might be worth exploring in the data why that might have happened. The important thing about Q-sums is it's the gradient that is giving you the information. And in this particular case, I used the average of all the data to construct the Q-sum. You can use other numbers, but if you use the average of all the data, then the rules that I've just mentioned apply.
Fantastic. If there are no more questions, I might bring this webinar to a close. On behalf of the AusIMM team, thank you very much for presenting. It was a great presentation. I'd also like to thank everyone who watched this webinar today and those who are watching this recorded webinar. For those watching live, if you can complete the exit survey, that'd be fantastic, and have a lovely afternoon.
Yep, thanks Alice. Thanks everybody for watching. I hope you found it useful.
Thanks, Tim.